All right, let's talk about equilibrium. When you hear the name equilibrium, what comes to your mind? Is it equal, equalize, equilibration, right? Things being equal, being to the same level? That is the right framework. That's what we're going to be looking at, but we're talking about chemical equilibrium. So we're talking about that type of mindset when it comes to not just chemicals, but chemical reactions. So what are we talking about? Well, it turns out that a lot of reactions that we've been looking at, a lot of natural reactions out there, when you take, let's say, A plus B gives me C plus D. It turns out that in nature, a lot of times, then C plus D give A plus B. Right? So the products can also generate reactants. These are what we call reversible reactions. Reversible reactions. Okay? And these reactions are exactly what it sounds right? The reactants give away to products and the products give away to reactants, right? Now, just kind of like a teaser, when the rate, we now know about the rate, which is the speed, right? The speed of A plus B giving C plus D, right? When the speed, the forward reaction, the speed of the forward reaction is equal to the speed of the reverse reaction, that's when we reach equilibrium. We reach equilibrium when the speed of the forward reaction is equal to the speed of the reverse reaction. So that is what we're going to talk about today. This chapter should be pretty short compared to the other chapters that we looked at. But again, like I already introduced to you, reversible reactions. We need to know about reversible reactions. And reversible reactions are reactions that do not go to completion. They go back. And most reactions found in nature are reversible and they depend on equilibria. Equilibria is just a fancy name to show that the plural of equilibrium. That's it. Just like bacteria and bacteria. But in a lot of natural reactions, especially the ones that are going on in our bodies, we depend on equilibrium. Now, let me ask you this. Why do you think that is? Why do you think a lot of reactions in nature like to go back? Well, the main reason is that if you have made things, right? If you have made things and you have made too much of it, guess what? You might need to go back. You might need to reverse so that you can recycle to get the original material, so that we can go back and forth over and over again. So we do that a lot in biological reactions, right? I'm a biochemist, so I deal with mostly biological reactions, and a lot of them are, in fact, reversible, and we're lucky for that. So equilibrium, right? Equilibrium is a state in which there are no observable changes. Right, let's make sure that I save this, because if it's not saved, then I won't be able to give you a separate slide. All right, so equilibrium is a state in which there are no observable changes as time goes by, right? So it has reached equilibrium. So we will be talking about chemical equilibrium, but there's also something called physical equilibrium as well. So chemical equilibrium is achieved when the rates, I already talked about this, the rates or the speed of the forward and reverse reactions are equal, and the concentration of the reactants and products remain constant, right? So that's chemical equilibrium. We're going from one thing to another, right? So an example is N2O2 becoming NO2. This is a chemical equilibrium. A physical equilibrium is when, so we are reaching an equilibrium, right? We are reaching an equilibrium. However, we are not changing the chemistry. So H2O may be coming from liquid to gas in a container, and then if the conditions are right, the gas can also be going back to liquid. Like for example, you've seen when you're boiling water, and then when the gas gets to the lid, it becomes liquid again, and then it goes back into the water. If you do that, we can reach equilibrium, even though we're not changing the chemistry of H2O. It's still H2O, we're just changing the physical states. That's why it's a physical equilibrium, right? Physical equilibrium. So when it is a physical equilibrium, we're only changing the physical states and we're not changing the chemistry. And when we have a chemical equilibrium is when you have a chemical reaction. We have the products and the reactants, and these are different chemicals, and they go back and forth, right? So that is the difference. So I want you to know the difference between chemical and physical equilibrium. But I want you to know something else, right? I want you to know another difference. It's difference between what we call dynamic equilibrium versus static equilibrium. So let me see if I have it here. So we have physical equilibrium. Yeah, so then you have dynamic equilibrium versus static equilibrium, right? So dynamic equilibrium is a equilibrium that's reversible versus the static equilibrium is the equilibrium that is irreversible, right? But most of these are chemical equilibriums. So again, very important, make sure that you know you have chemical equilibrium, physical equilibrium, then you have dynamic equilibrium and static equilibrium. So a lot of people kind of mix these up, so make sure that you know the difference. This is kind of how it looks like, right? So if we have N2O2 giving us NO2, the two arrows is how we show reversible reactions, right? By the way, let me make this point, and this is an important point, right? Not all reversible reactions are at equilibrium. We'll get to a point where I ask you like, hey, is this reaction at equilibrium or not? If it goes back and forth, it doesn't mean that it's at equilibrium. It's only at equilibrium if the back and forth reaction or the forward and reverse reaction have the same rates or same speeds, right? So that's when we reach equilibrium. So not all reversible reactions are at equilibrium, right? So make sure that you remember that. But they reach equilibrium, right? They reach equilibrium when, so look at this. This is a concentration graph, right? And with this concentration, you start with 0 product and then maximum reactants, right? And then guess what? Over time, the reactants go down, right? Let me use my pen. I'm not going to use. So the reactants go down, right? And guess what happens to the products? The products go up, right? But when we get to a point where they are no longer changing, right? When we get to a point where they are no longer changing, that's when we have reached equilibrium. I want you to notice something very important. And a lot of students make this mistake, right? They tell me that the equilibrium is the time at which the products and the reactants are at the same concentration. No, they're not, right? As you can see, they can be at different concentrations. It's just the time at the time at which they don't change anymore. As the reaction progresses, they don't change anymore, right? So they don't have to be at the same concentration, right? So this is an equilibrium graph when it comes to concentration, but let me show you a graph when we are looking at the rate, right? The rate of formation, right? And again, this is what confuses people, right? Reactants and products, right? Even though the concentrations are different, the rate here, which is the speed, is the same, right? The forward reaction, the speed of the forward reaction is going to be equal to the speed of reverse reaction, which is when we have equilibrium. But again, when it comes to concentration, right? Concentration and not speed, they will not be the same. One will go up, one will go down, but they will get to a point where they are at the same level. Not same level, but level that doesn't change. That's when we have reached equilibrium. I really want you to know the difference, right? Want you to know the difference. Very important, right? So initial rate is, it doesn't change, and then boom, it reaches a place where it changes, right? Does that make sense? Before you go forward, make sure that you understand what is equilibrium. How does equilibrium affect the products, the reactants, and then the speeds or the rates of the product and the reactants, right? And then what is a reversible reaction, right? And then after that, you're good to go. Because I want, those are big picture things that I want you to know before we go forward, right? And also make sure that you know the difference between chemical and physical equilibrium, as well as dynamic versus static equilibrium, right? And then now you are good to go to the next step. So the next step is equilibrium constant, right? If this is the first time you're hearing of this, that's okay, but equilibrium constant will come back over and over again in the future, especially if you decide to take more chemistry or biochemistry classes, because the equilibrium constant is what shows us how the equilibrium is going. Meaning, is it going this way? Is it going that way? Is it equilibrium so that it's equal, right? Now let me ask you this. This is kind of a hint or a teaser. If we are at equilibrium, right? If we are at equilibrium, what do you think the equilibrium constant will be? Meaning that if the forward and reverse reaction are equal, the rates are equal, what do you think will be the equilibrium? The equilibrium will be 1. The equilibrium constant will be 1, right? So what is the equilibrium constant? So let's say we have a reaction, right? A plus B equals C plus D, right? And then A, B, C, D are the coefficients, right? So let's say you have CH4 plus O2 gives us CO2 plus H2O, right? And then you gotta balance it, right? So we put 2 here, we put 2 here, then we balance, right? So if this is balanced, and let's say this is reversible, the real reaction is not really reversible, but let's pretend this is reversible. We make it reversible by making it back and forth. So the equilibrium constant, and you will see a lot of K's, right? In this chapter we will take about a lot of K's. KEQ, EQ is the equilibrium. The equilibrium constant, right, is going to be equal to the concentration of the products over the concentration of the reactants with their coefficients as exponents. You're gonna need to know how to reproduce this. Like if there's any math that we need to know in this chapter, any formula that you need to remember, this is the main formula, right? The equilibrium constant is going to be the concentration of the products over the concentration of the reactants with the coefficients as their exponents. So let's look at this. K, right, or KEQ or KC, C is concentration. So again, if you see a lot of K's with different little things down here, I want you to know the differences, right? Kc is the same as Keq. Kc is for concentrations. So it's going to be equal to the concentration of the products. Here, what are the products? Is CO2 is a product, and then H2O is a product. And look at that. H2O has a 2 in front of it, so it gets a squared over the concentration of their reactants. So the reactant is CH4, and then O2, and then this is going to be squared as well because O has a 2 on it. Does that make sense? That is how we give a equilibrium constant expression, right? So for any equation, make sure that you know how to write down its equilibrium constant expression. Very important, right? This is another way to show it, but my arrows have been shifted. So yeah, this is another example. There you go. All right. So this is another example, shows you, so N2O2 plus 2N2. So if I give you this equation is simple because it's kind of like A is equal to B, right? So it's like if I give you this and then I ask you the equilibrium is going to be equal to the NO2 squared because you have 2 on NO2 over N2O2 not squared, right? So that's the equilibrium constant. So for each equation, guys, so for each equation in chemistry, each equation will have its own equilibrium constant, right? Each equation will have the equilibrium constant, and it's a constant because it doesn't change across the reaction, right? So if you already found an equilibrium constant, it shouldn't change over time, right? And that is crucial, and we'll get back to it later. But the equilibrium constant does not change. Okay, so another thing to keep in mind is this, and this is important. After you found equilibrium, and I hinted it earlier, right? After you found equilibrium, the equilibrium constant, you should be able to tell me what it means for your equation. What do I mean by that? If the equilibrium constant is equal to 1, we are at equilibrium, right? If it's equal to 1, we are at equilibrium. If it's over 1, we go to the right, meaning that if it's over 1, we go to the right, meaning we're favoring the product. And if it's under 1, it's to the left, meaning we're favoring the reactants. So I will ask you, after you found your equilibrium constant, I will ask you like, hey, in this equation, is it going to the right or is it going to the left? And then I will ask you like, hey, in this solution, what do we have the most of? Do we have a lot of products or do we have a lot of reactants, right? So if it's if it's over 1, we have more products because it's going to the right. And then if we are under 1, it's going to the left. So the equilibrium constant here of this equation, what do you think it's lying? Where do you think it's lying, right? It's 4.63 times 10 to the negative 3, right? It's under 1. So since it's under 1, that means it lies to the left, right? It means that it's going that way. It's going that way. Rather than going forward, it's going reverse. And then if I ask you like, hey, what is the most prevalent entity in the reaction? You will tell me that it is this, your reactants. You have more reactants than products, right? So make sure that you know how to do that. So make sure that you know not only how to calculate the KEQ or KC, but to also tell me what it means, right? So how do you calculate it? Well, if I gave you the concentrations for this and concentrations for this, you just plug them into the equation, right? Now, in addition to Kc, right? So Kc again is K when it comes to concentration, right? Homogeneous equilibrium is when two things are in the same phase, right? Meaning, I don't know, they are all in gas phase or liquid phase or whatever. They're all in the same phase. We say homogeneous equilibrium, right? So these ones are all in gas. Now let me introduce you to a new type of K, right? And this we will need to know. So Kc is the KEQ we just looked at. C is concentration, right? C equals concentration, right? So Kc is the same, right? 802 square over N2O2. But Kp has to do with pressure. This is when you have gases, right? P is pressure, right? This is when you have gases. When you have gases, we don't use concentration, we use pressure. What type of pressure? If you remember, we use what we call partial pressure, right? Remember the partial pressures? So you use partial pressures, you still give them the right exponents. So in most cases, K of concentration is going to be equal to be different from K of pressure. And how do we reconcile that? By this formula, right? This is an important formula right here, which is Kp is equal to Kc times RT to the N, right? And the N will be the difference between the moles of gas products minus the moles of reactants. So for example, here, how many moles do we have? We have 2 moles of the products. You have 1 mole of the reactants that are gas, right? So delta N will be equal to 2 minus 1. It will be 1. Does that make sense? But again, if I gave you Kc is the one we mostly use, right? Kc is the one we mostly use because it has to do with concentration. That's the equilibrium constant. When somebody tells you calculate the equilibrium constant without specifying which one, you know they are talking about Kc, the one with concentrations. But again, when it comes to gases, you can measure them in terms of pressure, right? So Keq is the same as Kc, and then we talked about Kp as well. All right, so if I give you, for example, something like this, and that's another thing that I want you to realize, right? This is very important. It's very, very important, right? When we are measuring equilibrium constant, most of the time we don't use water. We do not use water. H2O. Why? Because H2O is not involved in the reaction, right? H2O is not involved in a reaction. So H2O is constant and is not involved in a reaction. So Kc or Keq of this reaction will be the concentration of this, right? Times the concentration of this over the concentration of this. So most of the time we ignore water because water is the medium, water is the solvent, water doesn't change, right? So instead of using this, we assume that the concentration of water is 1, we remove it. So Kc is going to be equal to this. All right, so we usually don't use water. So I can ask you like, hey, let me remove this. Right. I can ask you like, hey, the equilibrium concentration for the reaction between CO2, like this block, right? The equilibrium concentration for the reaction between carbon monoxide and molecular chlorine to form Cl2 at 7RCO. So they gave you the concentration for your reaction, right? Boom, boom, boom. And then calculate Kc and Kp, right? I like this one. Very straightforward, right? So you have the reaction is CO plus Cl2 is equal to COCl2, and then calculate Kc. What's Kc? Is the the equilibrium constant based on concentration, right? So it's going to be your product over your reactants, and then we don't have any coefficients here. And then guess what? You just plug in the numbers, right? The so-called COCl4 is 0.14, CO is this one, CO is this one. You plug in the numbers, and usually the Kc, we don't give it units, right? We do not give it units. And then here, the next thing is like, okay, what's Kp? Kp is equal to Kc times RT to the delta N, right? Remember Kc, we already found it here. R is a constant, T is the temperature that they gave us. You just gotta make sure when you have R, T is in Kelvin. When you have R, T is in Kelvin. And delta N is the number of gases, the differences between numbers of gases. So here you have 1 molecule of 1 mole of gas because it's just one coefficient. And then here you have 2 of them, right? So it will be 1 minus 2, which is -1. So Kp will be equal to Kc times R times temperature in Kelvin to the delta N, which is -1, and that will be your Kp, right? So that's how we find Kc and Kp. Make sure that you practice, right? You can use also partial pressures as well, right? You can use partial pressures. Again, here they can give you like the equilibrium constant Kp, right? They can give you the Kp, right? And then they give you they gave us the Kp, they gave me the Kp, they give me the temperature, and then they are asking you the equilibrium pressure of O2. This is actually an interesting one. When the pressure of this, so they want you to kind of reverse engineer it, right? So if we know this is the reaction, right? So Kp is equal to, for this reaction, is equal to pressure of NO squared, because NO has 2, right, times the pressure of O2 over the pressure of NO. The pressure of so the pressure of NO2 squared, right? Squared, why? Because NO2 has 2. And then guess what? They gave you the Kp, right? They gave you the Kp here, right? So they gave you the Kp. They gave us the Kp in the question. They gave us the Kp. They gave us the pressure of NO. They gave us the pressure of NO2, and then they're asking for the pressure of O2, right? This is NO2 is just shifted, so let's move it here. So this is NO2 here, boom. All right, there you go. All right, so literally it's just a after you figure that out, you're good to go, because you can just substitute, right? Your Kp is 158 is equal to PNO, which is 0.4 squared, right, times pressure of oxygen, which is what we're looking for. So let me make it X, over pressure of NO2, which is 0.27 squared, right? And then guess what? We have everything except X, so you can search for X very easily, right? Very, very easily. Now, what we call heterogeneous equilibrium is when equilibrium is not in the same state, right? So as you can see, after I fix this, right, notice how we have solid, right? Calcium carbonate is solid. When you heat it up, it becomes calcium oxide, solid, CO2 gas, right? I want you to realize something, right? The solids really don't change as much. The solids are constant. So CaCO3 is constant, CaO is constant. So what ends up happening is we don't use solids. We do not use solids in our formula, right? So usually the formula should have been this, the equilibrium formula, but if you have the solid, we don't use it. If we don't have a solid here, we don't use it. So the equilibrium constant will be CO2. So the concentration of solids and pure liquids are not included in the expression. Again, because they are constant, they don't change, they are pure, right? So we use what we call aqueous, AQ, right? So whenever you have AQ or gas, that's when you use equilibrium constant, right? Very important to remember. Let's look at another example. No, this is the same example. This is the same example. It's just that, again, when you have ACE, you don't consider it, right? So if I ask you, like, this is asking in terms of pressure, but if I ask you in terms of concentration, the Kc of this reaction up here is going to be equal to the concentration of NH3 times the concentration of H2S. I will not say over this NH4S. Why? Because it's solid, right? So if it's solid or pure liquid, we don't use it. We only use it when it's gas or aqueous. Why? Because those are the things that are mixed in the reaction. They are mixed in the solution. They can actually undergo the reaction. The other ones cannot undergo reactions. All right. So I think that's enough for these expressions, right? We can talk a little bit about this. Kc. So we have Kc, we have Kp. Let's talk about this one. No, this one I'm okay with that. Yeah, let's talk about this one. We'll talk about that, but so when it comes to kinetics, right? When it comes to kinetics, this rate, right? If you remember, when it comes to kinetics, these are rates, reaction rate, right? And rate constants. So these are different from equilibrium, right? These are different from equilibrium, if you remember, right? So don't get hung up with these K's, right? So remember that Kf or Kr, these are like, forward and reverse. So F and R is forward and reverse, but these are rate constants. These are not equilibrium constant. These are rate constants, right? So if you remember, the rate is the speed, right? So this is the rate of the formation, rate reverse, and then whenever you take the rate of formation over the rate of the reverse, that's literally what we're doing is the same as finding this, right? Which is the KEQ. This is how KEQ relates to the rates, but again, we're not going to go into like reaction orders and things like that, but that is how it is. So at equilibrium, by definition, by the way, at equilibrium, the rate of formation is equal to the rate of reverse, right? The forward rate is equal to the reverse rate, and because of that, if we equalize the two rates and then we divide them, we will get this, right? So at equilibrium, the forward rate over the reverse rate is equal to the equilibrium constant. All right, and if you remember, what's the number for the equilibrium constant at equilibrium? Do you remember what the equilibrium constant at equilibrium is? That's right, it's equal to 1. All right, so what another term that's called the reaction quotient, right? The reaction quotient is going to be calculated by substituting the initial concentration of the reactants and product into the equilibrium constant. So the reaction quotient is just using the initial concentrations of the reactants and products, right? So it's not the concentrations at equilibrium, it is the reaction, the initial concentration, right? So you see Kc as well. It's a quotient. We call it a quotient. It's a concentration quotient. So it's not an equilibrium constant. It's a concentration quotient. But at equilibrium, Qc is equal to Kc, right? That's at equilibrium. But when Qc is over Kc, we go to the right. When Qc is under Kc, we go to the left, right? So that's pretty much what determines that. All right. So let's look at a little bit of math. So how do you find the equilibrium concentration, right? So if I ask you, for example, there you go, boom, all right, there you go here, all right, now I feel better. All right, so if I ask you like, hey, at this many degrees, the equilibrium constant for this reaction is this. So I give you the equilibrium constant, right? I give you the initial reactions, the initial concentration, and I need you to pay attention, right? I gave you the initial concentrations, but they are not concentrations at equilibrium. They are initial concentrations. And we need to calculate the concentrations at equilibrium. And that, guys, can be can be a bit tough, but I will show you, okay? And let me delete this because it might confuse you. Let me delete this, and then I am going to just set it up from the beginning, right? So the reaction is this: Br2 as the gas gives to Br, right? So this is a simple one. One thing gives another, because sometimes you have two things gives one or something like that, right? So they're telling you that the initial concentrations, right? The initial concentrations of Br is 0.063 molar, and then the initial concentration for Br, but Br2, that was Br2, Br is 0.012 molar, right? So I want to introduce you to something, and I'm sorry that I might be the one introducing this to you, because some students don't like it, but that's the best way to do this. It's called the I stable. So I is initial, C is the change, E is the equilibrium. The I stable. With this, the I stable is what shows us it helps us to track the changes in equilibrium, the changes in concentrations as we go through equilibrium, because I is the initial. We already wrote them down, right? If we didn't have anything at the initial, if we didn't have any product at the initial, we would just write 0 at product. But then C is the change. So this is what shows us the change. And here's a crucial part in case you haven't noticed, right? The change in the disappearance of product is equal to the change. No, the change in the disappearance of the reactant is equal to the change in the appearance of product. So these changes are the same. It's just that this is disappearing. So how do we do that? We say minus a certain number x, and this number is going to be added here, right? So the change here, so this is minus x is plus x. That's the change. If we had another product, we would give it plus x as well. So this is minus x, this is plus x. as the ice table, right? So we are on the C. Then the equilibrium will be the initial, right? It will be the initial 0.063 minus x, right? Minus x. And then look at this. Here is 0.012 plus x. So at equilibrium, you will have these two entities in the solution, right? At equilibrium, you'll have that. And you're going back, they also gave me Kc, right? Kc is this. So the formula for Kc, if you remember, is the concentration of the product, Br, over concentration of the reactant, but with the exponents, right? So you gotta add the exponent here, right? And guess what? We do the same thing, but we now have the concentration. So what we're going to do is solve for x. So this is going to be 0.012 plus x squared over 0.063 minus x. And it's going to be equal to what? To the number that we have, right? 1.1 times 10 to the negative 3, right? So these are the numbers, and then we solve for x. Do you guys remember how to solve for x? Because this is going to be a quadratic formula, right? But again, you already know how to do that. I forgot very, very important detail here. Since we have 2 here, the change is not just x, it's plus 2x, right? Almost forgot. 2x, right? That way here you have 2x. That's an important detail. You have to remember your stoichiometry. So if you have 2 here, the change is 2x. So it's 1x here because you have 1 here, right? So after that, you have an expression of Kc, which is what we just did, is equal to this number. So we're going to multiply. We multiply here is equal to this, right? This is what we did, and then we're going to move it to the other side. So we're going to add this x to this x. We add this number to we subtract this number to this number, so that you are left with this quadratic formula equation. And if you can see, guess what? Quadratic formula equation. And I apologize again if I have to bring you back to this, because you must have taken this like in your algebra or some sort of whatever class you took. So I apologize if you were not a fan of this, but we're gonna have to know this again. And this is how we find x in a quadratic formula, right? If you have a quadratic formula that's this is how we find x. There's no way around it. Everybody has to remember how to do a quadratic formula. And again, it's going to be equal to negative b plus or minus square root of b square minus 4ac over 2a, right? And so you're going to be like, okay, what's my b here? My b, and you're gonna do it in your calculator, but I don't think your calculator can solve the quadratic formula equation. But your b here is this, right? This is your b. This is your a. Your a is 4. B is this number. C is this number. So you substitute your b, your a, and your c here, so that you can. And when you're going to put a plus number here and a negative number here, and it's gonna give you 2 numbers, right? It's gonna give you 2 numbers. But when you use these 2 numbers, right, one that uses positive, the one that uses negative, so after you find x, right, the concentration at equilibrium, look at this, the concentration at equilibrium will be this number minus x, and then this number plus 2x. That will be the 2 concentrations at equilibrium. When you use your 2 x's that you found, and then you plug them in here, as x, one of them will give you negative values, and we don't have negative concentration values. So that will be the one that you discard, because again, of the two values that you get, one is right, one is wrong. So again, if you don't remember your quadratic formula equation, make sure that you go back. Again, like I said, this is going to require a little bit of math, and that math is the requirement to get into this class. So if you got into this class, it's already assumed that you know that math. And if you don't remember it, I assume that you can go back and kind of remind yourself the quadratic formula equation. If I were you, I would just watch a YouTube video about it, but I'm always happy to walk you through it a little bit more, okay? But we definitely absolutely need to know that. But let's switch gears and talk about another important concept when it comes to equilibrium, and this is called Le Chatelier's principle. Le Chatelier's principle. And we like Le Chatelier's principle because it tells us what happens to a certain equation at equilibrium, right? So what it's saying is like, hey, well, actually, let me just tell you like what it's about first. The Le Chatelier principle tells you what happens to the equilibrium when we change the conditions. So does it go left, does it go right, or does it stay the same when you change the conditions? So in this chapter, I'm going to introduce you to 3 things that we change, and then we're going to see if we change those 3 things, what happens to the equilibrium. All right. So the first thing is concentration. And this is the principle, the Le Chatelier's principle, and the one that we're going to be using is saying that if an external stress is applied, if you add an external stress to a system at equilibrium, right, the system will adjust in a way to offset that stress to reach a new equilibrium position, right? I really want this to make a bit of sense, right? So if you add something to a solution, the equilibrium will shift to the left, to the right, in order to try to mitigate that drastic change. All right. Right, I think I have a better PowerPoint actually to show this. Hold on. All right, check this out. So you can change the concentration, you can change the pressure, you can change the temperature, and whenever you do that, the system will react accordingly, right? And another way to think about it, this is the PowerPoint that I was talking about. Think about it as like a balance, right? So you have these balance, they have the same amount, right? If you add more to the right, if you add more to the right, if you add more here, meaning if you increase the concentration of the reactant, guess what happens? The equilibrium is going to shift so that we can convert more, so that we can increase the reactants, so that we are equal. So if you increase the concentration of the products, no, the reactants, right, the equilibrium will shift to the right to equalize. Right? Same if you increase the concentration of the product, or if you add more things to the product, the equilibrium will shift this way to compensate so that we are equal again. So that's one way to think about it, right? Same with, yeah, this is the other one, right? So that's how to think about it. That's how to think about it. And that's, I think it's a good, I like this PowerPoint. I like this PowerPoint. And the same with pressure, right? So these are going to change. So if I ask you like, hey, if I increase the concentration, so if I can give you an equation like A plus B equals, and then, you know, arrow because it's reversible, C plus D. And then I can ask you like, hey, if I increase the concentration of B, if I increase the concentration of B, how does the reaction shift? The reaction is going to shift this way, right? So that it can reduce the amount of B, right? It goes to the right. If I increase C, it goes to the left, right? So that is concentration. But what about temperature? What about temperature? Do you guys know the difference between endothermic versus exothermic reactions? Let me go back to the other PowerPoint. So an endothermic reaction, right? No, this is not what I was looking for. All right, so an endothermic reaction is a reaction that really doesn't explain it either. Okay, so an endothermic reaction is a reaction that releases heat. No, absorbs heat. Endothermic absorbs heat. Exothermic releases heat. Right? So because of that, like, think about this, right? If a reaction increases heat or is exothermic, when you increase the temperature, how does the equilibrium react? Because so if a reaction is already increasing the temperature, right? If the reaction is already giving out it, increasing the temperature of the solution because it's exothermic, it gives away heat. Then if you increase the temperature, guess what ends up happening? It's going to shift in a way to reduce the temperature, so it goes to the right. So not to the right, but to the left. So they say you have A gives away B, and this is an exothermic reaction, right? Reversible exothermic reaction, and because it's exothermic reaction, it gives away heat, right? So it gives away heat, right? So if it's exothermic and then you increase the temperature, the reaction will react in a way that decreases the temperature, right? So in an exothermic reaction, if you increase the temperature, it will react by going that way. And guess what? If you decrease the temperature, it's going to go the other way. So this is what it's saying. So if you increase the temperature in an exothermic reaction, K decreases, meaning we go to the left. But in an endothermic reaction, a reaction that absorbs heat, right? A reaction that absorbs heat, if you increase the temperature, is going to go to the right. Right? And then the opposite is true. If you decrease the temperature, right, in an exothermic reaction, it's going to go in this way to increase it even more. And then if you increase the temperature in an endothermic reaction, it's going to go this way to counteract that change. All right. So I think I have a table of all the changes here, right? But again, it's still the same idea, right? For concentration, it changes the equilibrium. Pressure, like we said, it changes equilibrium. Volume changes equilibrium. Temperature changes equilibrium. A catalyst If you remember when we talked about a catalyst, catalysts are just things that speed up the reaction faster or slower. And this is a good multiple choice question. But a catalyst helps you reach equilibrium faster or slower, but it does not affect the equilibrium. Catalysts do not affect equilibrium, right? If you remember, catalysts lower the activation energy. So you start with a large activation energy, they lower the activation energy. But because we start and end at the same point, so catalyzed and uncatalyzed reactions, we start and end at the same point. That's why it doesn't change the concentrations or equilibrium, right? But look at, for example, so the temperature will change it, the volume will change. So this is the table I was looking for, right? If you increase the pressure, so if you increase the pressure or the volume, actually this is an important point. This is an important point that I almost forgot to say. The pressure and the volume, the way they shift depends on how many moles you have, right? So this is in the gas phase, right? What? This is for the concentration. Okay, so they didn't give us an example, but I give you an example, right? They say we have, what was the other gas? Okay, yeah. So we have Br2 gas becomes 2Br gas, right? So as you can see, it's 1 mole giving you 2, right? So look at this. When you increase the pressure, will it shift left or right? So if I ask you the question, if you increase the pressure, will we shift left or right? If you increase the pressure, the reality is that we are going to shift the equilibrium to the side with the fewest mole of gases. Why? Because if you remember, the pressure has to do with the disorder, right? So we're going to reduce the number of moles of gases. So it's going to go that way, so that we go from 2 moles to 1 mole and reduce the pressure. So if we increase the pressure, we're going to shift to the side with the lower moles of gas. So we have 1 mole of gas here, 2 moles of gas. If we decrease the pressure, it's the opposite. How about the volume? If you increase the volume, right? If you increase the volume, this is actually, one thing that you should know from your other chapter. But if you increase the volume, what happens to the pressure? If you increase the volume, the pressure goes down. So if the pressure goes down, we're going to shift in a way that's trying to increase the pressure, meaning that we go in a way that has the most moles of gases, right? So if you were to increase the volume, right, and think about this, if we were to increase the volume on my reaction that I drew here, right, if we were to increase the volume, do you think the equilibrium will react by going to the right or to the left? Well, if you remember, if you increase the volume, you lower the pressure. So the reaction will shift in a way to increase the pressure. How do we increase the pressure? We increase the number of moles. So if we increase the volume, the reaction will react by going this way. All right. So again, we need to know how the concentration, the pressure, the volume, and the temperature changes when we introduce something. Changes the equilibrium. When we change the concentration, the pressure, the volume, or the temperature, how does the equilibrium change? And I will definitely give you different reactions and different scenarios and ask you like, hey, does the equilibrium shift to the left and to the right, or to the right? And then I might even be tricky and ask you like, hey, what do we have the most after equilibrium? Do we have most reactants or most products? Well, we know that when we shift to the right, we are making more product. When we shift to the left, we are making more reactants. So that should be easy. That should be very easy, but that is what I have for you in terms of equilibrium. And look at that, we are exactly at 1 hour mark. All right, I will see you in the next one. Bye bye.